Good afternoon, everyone. With your fuel, coffee, and biscuits and so on. I've been at EA Technology 6 years and worked on various energy storage projects in that time. So that's technical and safety assessments of different systems, and also working very closely with the network operators through the Energy Storage Operators Forum. EA Technology then are a power engineering consultancy, so we support energy networks, primarily electricity networks, but a bit of work on gas as well. And energy storage is really part of the whole range of work we do on network innovation. So we've been working quite closely with a lot of the DNOs through the low carbon network funding projects and then into the network innovation allowance as well. Since I work on storage then, we had a period when we were mainly working with the DNOs through that low carbon network funds kind of time. We're seeing a bit of a change now into more industrial customers rather than DNOs only operating storage. So what I'm going to cover today then is a bit of background to the Red Sea Flow Battery Demonstration Project. I'll talk about the technology which is being deployed, some of the challenges and how they've been overcome, and then summarise what the next steps are for Gigha and also for Red Sea systems realised widely. So there's a whole range of partners in the consortium for this project. Red Sea at the top, they've got 15 years of development work on the stack technology. It's their product. Ourselves, providing consultancy support, project management and acting as client engineer. Gigha Green Power Limited, which is the logo there. They own the wind turbine on the Isle of Gigha, and that's a community-owned and operated company. Consustant Southern Electricity Networks, as they're now called, since about last week. They're the distribution network operator for the island, so they have an input in the project throughout the whole of the project, but most recently on the factory acceptance testing and looking at the network protection aspects as well. And there's also Community Energy Scotland, who provide support for a range of different community projects. And I'll talk a bit more about the kind of community aspects of this particular deployment a little bit later. So this project was one of 4 that was funded by the Dudek energy storage demonstration competition that was launched in 2012. And it was awarded £3.6 million for the development of 105 kilowatts 12-hour battery. Initially, the primary aim for that was to remove a constraint, or lessen the constraint that applied to the 4th wind turbine on the island. And also, it's, as I said, it's a community-based project because the wind turbines on Gigha are owned by the island's residents. Primary aims then were to take Red Sea stack technology and scale that up to grid demonstration, integrate that into a complete product, so rather than just being individual stacks, of a whole system with power conversion system and all the interfaces around that. Design that for manufacture, so this isn't going to be a bespoke thing that's been put together specifically for this demonstration project. What they're aiming for is a product that can then deploy elsewhere as well. And obviously install the system at Gigha and show the constraint being overcome. So this gives you a little bit of context to the lovely Isle of Gigha. Put on the right is a little map of the location, so the tiny island in the circle there. About 60 miles west of Glasgow, and there's a population of 150. I think the main industries is tourism. There's also a fish farm as well. The whole island is community owned, and the revenue that they get from the 4 wind turbines support community projects on the island. The rating of those 4 turbines is over 1 megawatt, but grid constraints that were in place meant that the newest turbine on there had its output limited to 235 kilowatts, which is 105 kilowatts less than its rating, and obviously with the equivalent lost energy over the lifetime of the turbine. The community element for this project was really important, both in terms of delivering it, because without the community buy-in and being able to deploy it with those turbines on here, there isn't this demonstration project. There's also an important role in terms of shaping the direction of it and quite a difference between, say, working with a large renewable developer. The resources that Gigha has got to do this project are less. The engineering expertise available is also obviously going to be different, and their ability to tolerate risk is different as well. So looking at the technology in a bit more detail then, fundamentally what's being done in this project is taking the red tea technology from a concept, from a lab, slightly bigger than a lab scale demonstration. I went to them in 2013 where they had a single stack operating within their industrial unit in a sort of industrial estate in Wokingham, and they're now moving to a full containerised product. So the outset of the project then, the chemistry was proven, so they had the stack working in Wokingham for several months, but the system that goes around that, its manufacturability, its reproducibility was all still to be proven. Initially, the concept for Gigha was going to be to put it in a building, and the architect on the top. And during the length of the project, that was radically reworked to be a containerised solution, which is good news because it means you get something more productised. You don't have to then be looking at bespoke buildings for every time one of these is going to be implemented. It's a shipping and container model. We've seen quite a lot with battery technologies as well. Also, it's got benefits for easy maintaining or upgrading the system, so you could add an extra container, whereas if you were in a building, you'd be restricted in space. And in this instance, it helped with the planning permission as well. We've also had to work up all support systems around the core storage technology. That's covering things like their electrical connection to the network, the metering requirements, and all the mechanical and chemical systems that go with the battery system. As well as developing the technology then, moving from those stacks to a complete product, this project's delivered learning in other areas as well. So in terms of safety, health and the environment, there was a detailed review that was carried out by the local council and the Scottish Environmental Protection Agency, and an ongoing safety review by third parties, which is one of the roles of the project and where I've mostly been involved. For the safety side of things, a flow battery system is very different to the battery systems we've already talked a bit about earlier on. So in terms of lithium-ion batteries, in terms of raised around fire, thermal runaway and so on. In this case, storage medium is water-based, so those risks of things like fire and explosion and self-heating are very much reduced. But it is still a very large piece of equipment. There's still chemicals there. There's still chemical water-based things like electricity. So there's been a lot of effort into making sure all of that is properly down. And moving from that lab-based test system into a whole integrated system to be installed at the site, there's a series of electrical subsystems and different interfaces that are needed to have that complete product. So firstly, in this case, it needs to interact with the wind turbine. It needs to know what the generation output's doing, and therefore whether the strength applies and whether it should be charging or discharging. So there needs to be communication between turbine systems and the battery to do that. There also needs to be fail-safe put in place, so that if, for instance, the battery's offline, then that constraint still needs to be applied to the wind turbine because it will need to reduce its output because it can't store the excess into the battery. They're also connecting onto the distribution network, so they've got to satisfy the requirements of DNO, which is one of SSE's roles in the project. So that's around things like power quality issues that might be from the inverters, and also protection requirements, so making sure it performs as it should. Things like high voltage, frequency events and so on. And that's been part of the testing that's been done at the Networks Demonstration Centre. There's also a remote monitoring, control and diagnostics functionality in there. That's got safety functions, so it's things like alarms, low temperature, that sort of thing. It's also really important for what is a demonstration project that they can use that remote diagnostics and remote control during the testing phase. Also very handy when you're installing systems moving into the autumn on an island that's 60 miles west of Glasgow and quite remote, so they're going to be able to do some of those tests without essentially the engines of the system. So the stacks have the vanadium solution flowing through them. That's where the redox reaction occurs. That's where we get the charge and discharge. And each of those stacks is a 5 kilowatt unit. In the case of Gigha, we have multiple stacks in each container, so it's 3 for Gigha, but they can vary that to 2 different customers. So we're also looking at 5 kilowatt, 40 kilowatt hour units rather than the 15 to 40 units, which is what Gigha is built up from. And the bottom picture there is the units going to test at the Power Networks Demonstration Centre in Cumbernauld, where they've been undergoing testing for the last couple of months. Through the project, obviously there's been various challenges that have been faced that are specific to energy storage, which is what I'll focus on here. There's also a range of other issues about how you take a product and design it through for manufacture and deployment in this sort of time scale, but I'll focus on storage for here. The first one is around the feed-in tariff. For Gigha Green Power, the revenue they get from the generation element of their feed-in tariff is crucial. So it's really important that having a flow battery wasn't going to interfere with us in any way. And what's been secured here with Ofgem is an agreement that the generation fit revenue stands because what we've determined the storage is going to be an eligible load for this case, which is equivalent to saying I've got a wind turbine and I'm going to site it with my factory and use some of the energy from my wind turbine in my factory. They're doing the same thing but with a battery. We've also had to go through planning permission. So that's true for whether you're doing storage deployment or renewables. And in this case, for a remote site with a wind turbine, containerisation helps a lot. But obviously that's quite site specific. So if we heard about the latest buzzard battery earlier on, that isn't a shipping container example, but it's also right in the middle of the residential area. So having a building solution there makes a lot of sense in this case. Shipping containers is better for planning permission. There's also been a lot of work done around the energy purchase contract. The power purchase agreement's been arranged with Good Energy, and that's needed close interaction with Red T to put forecasts around what the battery will be doing so they can access variable energy prices. There's a change that needs to be made for Gigha so they can access the different time varying bands for distribution to system charges. I think somebody mentioned earlier on as well. And what that will do is increase the price differential they can access across the day, which means they can make more money out of arbitrage operation. Take those, add in things like triad avoidance, and obviously in the case of this constrained wind turbine connection, the value of the lost energy that they're now able to access, then you start to see the beginnings of a viable business case. And a big part of what Red Team are doing in their commercial work is understanding how you can maximise the utilisation of your energy storage system. So if you can keep this unit operating for as much of the time as possible, then you're earning as much revenue as possible. The items that are in grey in the bottom of there, we're also work done around those, and some challenges in that. But those really to do with this first of a kind deployment. So once we move into a more product-based system, that approach is really important. So what next then? They've just completed testing at the Power Networks Demonstration Centre. The press release came out about that a couple of weeks ago. So the next move is installing on Gigha and doing testing there. So that's initially proving trials, prove the system's operation, and its long-term performance in that whole integrated subsystem. It's worth saying that there's been that stack's been working remotely for a long time now, and that's showing really good performance figures. Then it's showing, once this unit's operational, how the revenue streams stack together and proving the business case. Continuing to roll out the smaller units, and we'll spoke about 5 kilowatt, 40 kilowatt hour units. Exploring, particularly in Gigha's case, whether you can use energy storage to make more resilient supplies. So this is a remote island with particularly kind of the extremes of weather that you would imagine on a remote Scottish island, stuff like the west of the UK, with their own generation and soon to be with their own battery as well. They do experience outages fairly regularly, so what they're interested in looking at is whether they can combine their generation and their battery to lessen the impact of that. So, sort of final question. This was taxpayer funded, £3.6 million worth of debt money. So, valid question, was it good value for money for the taxpayer? And we think it is, in that look at what's been achieved. It's moved a company from concept to production in 3 to 4 years, which was pretty fast acceleration in terms of what we're saying about the length of time for innovation, that kind of thing. It's been designed and built between Scotland and their original base in Wokingham, with supply chain throughout the UK. So that's what some of the pictures are showing in terms of development. So we've got the initial and the artisan collections of the containerised system. That is the first of where it's going to go. These are a couple of pictures from the factory where the stacks are being made. That makes the system from the installation. So everything's been put together in the factory. And now it's ready for testing at the NDC. It's also helped Red Sea secure private investment, so they've leveraged the debt-funded work to achieve private investment of at least the public funding, so that's covered the impact of that money. And in terms of UK PLC overall, a lot of the predictions we've seen on graphs of them earlier on have shown how large the market for energy storage is predicted to be going forward. And at the moment, particularly if you look at battery systems, that's being dominated by US firms, Southeast Asia. So if we can build up a UK supply base through companies such as Red Tea, then that's going to be hugely valuable moving forward. Thank you.
Oh, thank you very much. I apologise for the drilling. There's absolutely nothing we can do about it. The window's open automatically, and as far as I can tell, randomly in this place. So the only thing we can do is just bang them closed and weld them up. So I apologise for that. So I hope you'll be able to concentrate on this project. So questions, comments, observations, please?
You were saying that there's power outages quite often, and how long are those, or how long will this power the island, and how long are the outages normally? I know they went out for about 4 days a couple of winters ago.
Yeah, that was the one I was aware of. This is the point at which I confess that my involvement has mainly been on the safety side, so I'm not sure in terms of total island demand. Whether they could look at selective carrying of load with the other options is a really important thing going for long enough to balance what they can do with that. But at the moment, that kind of operating of the island, particularly in terms of the network operator's perspective of that, would be under the stage of development of it. I'm not sure what the power line on the island is. So it's 105 kilowatt 12-hour system. I think the capacity is in the 5 megawatt hour range. They were able to increase that. So the initial estimate was based on pushing the cell chemistry a certain distance through the development work. They've actually been able to get more out of that. So they're still able to project them. So I know I'm identified in there, but I'm not sure if what's mined on the island is there for how long it's going.
Any other questions? I'm going to take my prerogative. This was a £3.5 million project, is that? Roughly what percentage of the money was spent actually, was spent on the energy storage system itself, as opposed to all of the inverters and transformers and things that go around it?
I'm not sure, I'll find out.
Because it's sort of 95% or 5%, or roughly, just a rough figure.
I'm really not. I wouldn't know enough to be able to give you a
figure.
I know it's been something that has been published on other projects in terms of what the split is between the battery technologies and the health plants stuff as well.
Yeah, no, it's. I think it's instructive to think that the Sheffield battery was 5 million, and roughly 80% went on the balance of plant inverters, and only 20% was spent on the energy storage itself. So, if you look at it from this point of view, energy storage isn't that expensive once you've got the infrastructure in place. Yeah. So, any other questions or anything like that? No, well, thanks once again.